Chapter 4, Applications of Differentiation. My name is Matthew Newbeck, and these slides correspond to Stewart's calculus book, Early Transcendentals, 8th edition. In Chapter 4, Section 1, we're going to talk about maximum and minimum values. My strategy in this particular video is I'm going to walk through these slides with you, which were prepared by the author, and I'm going to put some little notes on here, and you can pause and take some notes as we're going along, and then I'm going to switch over to a notepad and work a couple of example problems for you. But let's just get acquainted initially with the idea of the max and min and talk about a couple of key sort of vocab words and phrases. So on this slide, we're talking about exactly what we mean by a max and a min, and we're talking about the highest point and the lowest point on a graph. That doesn't seem super challenging conceptually. Over here, we're looking at the maximum. Here is the minimum. Slide says, in other words, the largest value of f is, and remember that f of 3, when we see this, that's a y value. So here we're saying that there's a y value of 5, and that y value happens when your x value is 3. And of course, if we look up at the graph, we can see that happening. There's the point 3, 5. Likewise, the smallest value is f of 6 equals 2. The smallest value is 2. This, on the left-hand side of this little equation down here, that's a y value. On the right-hand side is a y value. In the first little equation that we looked at, this thing that I'm circling here, y value, y value. So when we're talking about maximum and minimum values, largest values, smallest values, what are we talking about? We're talking about y values. We're definitely interested in when they happen. This largest value happens when x equals 3. The minimum value happens when x equals 6. We say that f of 3 equals 5. We say that that y value is an absolute maximum of f. So f is the name of our function. It's the title of the graph, so to speak. It's not a specific value. It's the whole thing. Right? So the absolute maximum, the largest y value, is 5. We just talked about that. And 2 is the smallest one. And we call them absolute maximums and minimums because that brings us into this definition. So here, an absolute maximum is a value, a y value, as we know, of our function. In this case, it's f on D. So there are a group of x values that we're going to be examining, and that interval is going to be called D for the moment. And it's the largest, or it's the absolute maximum, if the y value that happens when x equals c is greater than or equal to the y values for all other x values. So, technically speaking, the y value that you're talking about doesn't actually have to be greater than or higher than all other points. Let me just draw a quick sketch to say, if we're looking at this graph where our x values are going from here over to here, and on our y-axis I've got 1, 2, 3. What is my absolute maximum? It's the biggest y value. What's the biggest y value on the graph that I just drew? It's 3, certainly. Now, when does it happen? Does it happen at one distinct c value or at one distinct x coordinate? No, it happens for a whole bunch of different x coordinates. All the x coordinates from here over to approximately here. But that doesn't change the fact that there's only one absolute maximum, absolute largest y value present. And we could have the same kind of a conversation about absolute minimums. As we continue reading, an absolute maximum or minimum is sometimes called a global max or a global min. Maximum minimum values of our function are called extreme values. So just a little bit of verbiage that we might see as we're going along. Some different terminology that's used. All right, so now we're looking at figure 2, which shows the graph of a function. It has an absolute maximum at d. So remember, d is when it's happening, and f of d is what's happening. It's the y value of that coordinate, f of d. It's a terrible f. Maybe that's worse. So d comma f of d, it's the highest point on the graph. A comma f of a is the lowest point on the graph. There it is. If we consider only values of x near b, so now we're going to focus just on, let's get rid of all these other distractions. We're going to focus just on x values near b. So we're in here. So we're restricting our attention to that interval. Oh, the author's saying this interval that goes all the way from A to C. Then f of b is the largest of those y values and is called a local maximum. So again, the y coordinate of this point, and that point is b comma f of b. There's a local maximum that happens there, and that local maximum is f of b. It's the y coordinate there. But it's a local max because we're only focusing on points or x values that are on a particular interval, not the entire graph, which may well go all the way to negative infinity and positive infinity. So local max. I like to think of it as I'm standing at the top of a hill. It would be a local minimum if I were at the bottom of a valley. Because if you look at the y coordinate here, and I'm sure I'm jumping the gun, what's the y value here? It's the lowest of the nearby points. However, its y coordinate is not as low as this y coordinate, is it? So it's not the absolute minimum, but this over here, f of e, is a local minimum. So here's a formal definition of local max and local minimum. Local maximum is the value of f if the y values are greater than or equal to nearby y values. So y values that are near the x coordinate of c. And c, this c right here, is a specific undisclosed x coordinate. It's not a variable, it's a constant. Definition 2 and elsewhere, if we say that something is true near c, that means that there's some open interval containing c. So if we're on a number line, and maybe here's 0, and here's some arbitrary value c, and we're on some open interval, maybe we're looking at x values that are between here and here, that open interval contains this x value of c. Open interval? Yes, that's why I've put parentheses in order to define this portion of the number line. A closed interval would have square brackets on it, and you can think of that as being inclusive, like a shaded circle, as opposed to parentheses, which are like an open circle, excluding the endpoint values. So again, we're on an open interval, which means we are using parentheses, or, oh, that got rid of everything. which means that we're using parentheses. Some of us call them open brackets, excluding the endpoints of that little interval. Maximum and minimum values. For instance, in figure 3, we see that when x is equal to 4, we have a y value that is 5. It's a local minimum because it's the smallest value of f on the interval I. And they've labeled the I right here. So our interval there is going from 3 up to 5. That's our interval. And it's the lowest point in that neighborhood, so to speak. We've got a local maximum here because it's the highest point in that neighborhood on interval j. This point is unique because not only is it a local minimum, it's the lowest point on interval k, but if we look at the big picture, it's also the lowest point out of all of the points. So that makes it an absolute minimum also. So it's a local and an absolute minimum. Maximums and minimums. Who thought that there would be so much to say about maximums and minimums? It's not the absolute minimum because f of x takes smaller values when x is near 12 in the interval k, for instance. Similar local maximum, but not. Really, I think we've covered all this. You can go through and read this if you like. I just gave it a quick glance. I don't know that necessarily it helps more than what I said already. However, so I'm going to stop, and I'm not going to cover that slide. If you would like to read it, however, and get some different language to describe what I was just describing, by all means you should read that, and if it works better for you, then go with that. Here's an example provided by the author that says that this function f of x equals cosine x, and here's the cosine graph. We can see it going up to its highest point, down to its lowest point. But this is interesting because the maximum, or the largest y value of the basic cosine function is 1. Right? The range of the cosine function goes from -1 up to +1. These square brackets tell me that I'm including those endpoint values of -1 and +1. But they happen over and over and over again. This point has a local maximum of 1. This point has a local maximum of 1. The entire graph forever in both directions, the largest y value that we're going to encounter is 1. And this is saying that since the cosine of 2n pi, where n is an integer, is equal to 1, our y values live between -1 and +1 inclusive. So that's saying the same thing that I was saying here. It's describing the range. And the minimum values it's saying at the bottom of this slide for the cosine function are -1, and they occur infinitely many times. For example, this point here at pi hits the local minimum of -1, and then if you add 2 pi, which is the period of the cosine function, you arrive at another point with a different x value, same minimum. It's a local minimum. It's also an absolute minimum. Just like those maximums were also absolute maximums. It's the largest of the y values, no matter how far to the left or right you go. All right, so now we're on to this slide, 8 of 18. The following theorem gives conditions under which a function is guaranteed to possess extreme values. It's called the extreme value theorem. And let's look at the components of this statement. F is a function. It's continuous, which means it doesn't have any asymptotes, it doesn't have any holes, there's no discontinuity. It's on a closed interval, so we are going to potentially be examining the endpoints. So if it's continuous on a closed interval, then the function will attain an absolute maximum value. Remember, this is a y value, and an absolute minimum value. here's another y value, f of d and f of c, at some numbers c and d in our interval that goes from a to b. Some illustrations of that extreme value theorem. Looking at the first graph on the left, from a to b, right? Our graph goes from a to b. Is it a closed interval? It sure is, because we've got these closed circles, these colored in dots right here. So it's closed interval. And is it continuous? Absolutely. There's no asymptotes or holes. Is there a maximum? There sure is. It happens when x equals c. Is there a minimum? Definitely. It happens when x equals d. Okay. In our second graph, the one in the middle, again, our maximum occurs when x is equal to c, but interestingly, our minimum happens when x equals d. At least that's what we were saying, sort of generally speaking on the previous slide, but it just so happens that it's happening at our end point. It happens when x equals b. Good thing we're including that b value on our closed interval. So it's possible that a minimum or a maximum could happen at an end point. Here, in our last example, the graph on the right, we're seeing that the maximum value happens at C1, and that same maximum value is happening at C2. Does that change the fact that there's one absolute maximum value, that there's one y value that is reached that's bigger than all other y values at this point, or at this point, or at this point, or at this point? Nope. There's still only one absolute maximum. It just so happens that in this graph it happens twice, or for this function it happens twice. And there is still a local minimum happening when x is equal to d. Functions that are continuous on a closed interval always attain extreme values. Extreme values that happen once, extreme values that happen twice, extreme values that happen in the middle or potentially at the end points. It's all over the place. And we're going to have to keep that in mind shortly. Figures 9 and 10 show that a function need not possess extreme values if either hypothesis, the continuity or closed interval, is omitted from the extreme value theorem. In other words, if you're not meeting the criteria of the extreme value theorem, you're not necessarily going to possess, or your function's not necessarily going to possess, extreme values. Look, this function on the left is not continuous, and as a result, there's no maximum value. What do you mean? This looks like the highest point right here. I did call that a maximum value. Well, what's the y coordinate right there? Well, you might say that it's 3, but it's not, because that open circle tells me that there isn't actually a point there. So as we follow our curve, our y values are getting larger and larger and larger and closer to 3, but we never actually quite get to 3. So I can't say that I have a very distinct maximum value. You can't quite get there. In the example on the right, this is not, well, it's a continuous function, but it's not on a closed interval. Notice the open circle at the left end of the interval, that's discontinuity. Notice the asymptote that's over here, that's the other type of discontinuity. So we've got a nice continuous graph, except it's on an open interval. This lowest point down here on the left, what's the y coordinate there? Don't know. Super close to 1, but not quite 1. And what's the largest value over here? Something really big, okay? Not a real number. So because we've contradicted the extreme value theorem in these two examples, we're not necessarily going to end up with extreme values. So this slide is talking about what we were just talking about in the previous slide, getting arbitrarily close to 3, and on the next slide we're talking about that open interval and that the range gets really close to a y value of 1 down here, and the range, the y values go really far up there toward positive infinity, but you can't call positive infinity a maximum value because positive infinity is not a real number. It's an extended real number, which is not a conversation that we're going to have in this video. So the extreme value theorem says that a continuous function on a closed interval has a maximum and a minimum value. Great. But it doesn't tell us how to find these extreme values. On this particular figure, figure 11, look at the location of these extreme values. Here we are at the top of a hill, C comma f of c, and at the bottom of a valley, D comma f of d. Right, that looks reasonable, but how am I supposed to find those? Well, there's this sort of magenta line that's drawn here for us that passes through both of those points, the maximum and the minimum, a relative max, relative min. How would you describe that line, that magenta line, both of those lines? The key word is horizontal. And what's the slope of a horizontal line? 0. And is it a tangent line also that's being drawn there? It sure is. So this is a horizontal tangent line. It's a tangent line with a slope of 0. Slope of a tangent line? I think we all know at this point that that is synonymous with the first derivative. So that's what's being articulated on this next slide. It appears that the maximum and minimum points, the tangent lines are horizontal, slope of 0. Derivative is the slope of a tangent line. That's what we were just saying. So it appears that the first derivative when x is equal to c, in other words, the slope of the tangent line is equal to 0. And the first derivative of our function at d is equal to 0 because the slope of the tangent line is 0. In other words, it's a horizontal line. The following theorem says that this is always true for differentiable functions. If our function has a local maximum or minimum at a particular x value, and if the derivative of our function evaluated at that x value exists, then that first derivative evaluated at that x value will be 0. That's what we were just seeing in the previous illustration. Does that always work? Unfortunately, as we see in figure 12, if we look at the graph of x cubed and we take the first derivative of it and we get 3x squared, and we were to set this function equal to 0, we would find out that the first derivative of our function equals 0 when x is equal to 0. And here it is. Look, I can draw my own magenta line right through there. It's horizontal, which means that the slope of the tangent line right here is 0. But is that point a maximum or a minimum? It's not. So we're seeing that at some point in time, as we start working problems, we're going to have to be careful because it's not necessarily the case that if their first derivative is equal to 0 at a particular point, that you're going to have a maximum or a minimum. In the case of y equals x to the third, the curve simply crosses its horizontal tangent line there. It does have a horizontal tangent line, but it's crossing that tangent line, which is a little unusual. On this slide, we're seeing example 6 with the absolute value function. And while the absolute value function does have a relative minimum, a local minimum, and an absolute minimum, you can't find it by taking the first derivative and setting it equal to 0 because the absolute value function is not differentiable at x equals 0. To be differentiable there, it would have to be smooth and continuous. It is continuous, but it's not smooth. It has that sharp corner on it. Here, we've got a slope of -1 or +1. All of these points have a slope of -1, and those two slopes aren't approaching the same slope. Therefore, at least that's one way that we could say we can't sort of decide what the slope is at that point. Smooth and continuous. Absolute value function is not smooth. It's sharp at its vertex. So it's not differentiable there. Examples 5 and 6 show that we have to be careful when using Fermat's theorem. Example 5 demonstrates that even when our first derivative is equal to 0, there's not necessarily going to be a max or a min. And you might have an extreme value even when your first derivative does not exist, as was the case with the absolute value function. Fermat's theorem does suggest that we should at least start looking for extreme values of our function where the first derivative of our function is equal to 0, or perhaps where our first derivative does not exist. Those particular locations, or I could say that the x values of those particular locations, are called critical numbers. So this is a key word that we're going to be using and seeing in questions. The critical number of a function f is a number c that's in the domain of our function such that either the first derivative is equal to 0 or the first derivative does not exist. And then the author rephrases Fermat's theorem and says that our function f has a local maximum or a minimum at c, or rather if the function has a local max or min at some particular x value, for example c, then c is a critical number of f. I think that's a fine way to phrase it. And then there is the closed interval method, and this is what we're going to be using in our example problems. We need to know these 3 steps. It is necessary that we know these in order to be successful, especially going through this chapter, this section for sure. So step 1 is we want to find the values of our function at the critical numbers on the open interval. So we're going to be operating on a closed interval, except we're only going to look for critical values on the open interval, and then we're going to address the sort of square brackets on that closed interval by finding the values of our function at the end points of the interval. And then we're going to make some comparisons of the values that we find in steps 1 and 2 in order to determine the absolute maximum and the absolute minimum. All right, I do have some problems queued up. In problem number 3 from the homework set that I'm assigning to go along with this section, we're asked to find the absolute maximum and minimum values of a given function. I really do hate writing with a digital pen. You're going to hear me say that frequently, probably. Alas, this is the problem that we're working with. We want to find the absolute max and min of our function on this particular interval. 4x to the third minus 6x squared minus 144x plus 9. Let's go through the steps. The first thing we want to do is find the first derivative. So let's find f prime of x. 3 times 4 makes 12, and we'll decrease the exponent by 1. So we've got 12x squared minus 12x to the first power, the 2 times the negative 6. There we go. And minus 144, x to the 0. So that turns into multiplication by 1. The derivative of a constant turns into a 0. So we don't need that. Great. Now we want to take our first derivative and set it equal to 0. I'm going to divide this entire equation by 12. This is a little note about what I'm going to do to both sides of this equation. I'm left with x squared minus x minus 12, still equal to 0. And then we need to solve this, so let's factor. X minus 4 times x plus 3 is equal to 0. So we get solutions of x equals 4 and x equals negative 3. So these are the 2 critical values, and we'll notice that both of these, let's put a little note, both in the closed interval from negative 4 to positive 5, so we are going to consider both of those. And the next thing I'd like to do is evaluate our function, f at critical values and endpoints. It's a good thing I'm saying it and not just writing it, or you'd be totally lost if you had to only read my handwriting. So let's work our way through from left to right. F of negative 4 is 233. Our next largest x value is negative 3, and f of negative 3 is equal to 279. Next largest x value that we encountered is 4. F of 4 equals negative 407. And finally, f of 5 is equal to negative 361. The largest of the values that we see here, this is the absolute max of, so if I asked you, what's the absolute maximum? The answer is 279. When x equals negative 3. So this is what happens, and this is when it happens. The absolute minimum of negative 407 happens when x equals 4. And that is the solution to our first problem in 4.1, finding maximum and minimum values. Let's see if there's one more question that would be good for us to work out. Let's try this one. This is number 6 in the homework set that I'm going to assign. Find the critical numbers. So, for example, of the function f of x equals x to the third times e to the negative 6x. In order to determine that, we need to take the first derivative. So let's change colors. F prime of x equals. We're going to use the product rule and the chain rule here. So this is my first factor, this is my second factor. So I'm going to keep my first factor, x to the third, and multiply by the derivative of my second factor, which is e to the u du. So we keep e to the negative 6x, and then we multiply by the derivative of the exponent, which is negative 6. Product rule says then we add. We take the derivative of the first factor, which is 3x squared, and multiply by our second factor, e to the negative 6x. And then we have the great pleasure of setting this equal to 0. I think I might rewrite this one more time just so that it's a little cleaner. So I have negative 6x to the third e to the negative 6x plus 3x squared e to the negative 6x. And we're setting that equal to 0. And what I'm really hoping, bring out my algebra skills, I'm really hoping I can factor something out of here and turn the left-hand side of this equation into something times something equals 0, so that I can set both of those somethings equal to 0, just like we did up here. Something times something equals 0. We set each one of these equal to 0, and that's what gave us these two critical values. All right, so let's factor. We could divide this entire thing by 3 or negative 3 for starters, but let's take out, how about a positive 3 and an x squared and an e to the negative 6x. And the leftovers, as I like to call them, are a -2 and an x and +1. We factored out that entire second term. All right, so now we sort of have what I was hoping for, but instead of the product of two things equal to 0, it's the product of three things being equal to 0. Here's one factor we're going to set equal to 0. Here's another one. And here's a third one. So let's do that. I'm going to take 3x squared, set it equal to 0. E to the -6x equal to 0. And finally, -2x plus 1 equal to 0. Surely, this turns into, when we divide both sides by 3 and take the square root of 0, we get an x value of 0. Oops, that got away from me. It's not possible to take a positive number and raise it to an exponent and get an answer of 0. This is never going to be true. So then we examine our last statement, subtract 1 from both sides, divide both sides by -2, and we get an x value of 1/2. Are these our critical numbers? Well, we didn't have to adhere to any constraints. We weren't trying to find the critical numbers on a particular interval, so I like to put boxes around my final answers so that they don't wander off. Those are your two solutions. Maybe the tricky part was getting rid of that middle statement because it's never equal to 0. Regardless, stay organized on this stuff. Don't forget your algebra skills. The product of any number of things being equal to 0 requires you to take each one of the different factors and set them equal to 0. Your critical numbers are where the first derivative is equal to 0. That's all I've got for you for this section. Thank you so much. I will see you in section 2.